I am Anil Kumar. Welcome to my series on trigonometric identities. In this unit, we have learned about the fundamental trigonometric identities. We have also seen how to use these identities to simplify expressions, to solve equations, and to prove identities. Based on our learnings, here is your very first exam preparation test. We'll begin with sharing with you the list of formulas on fundamental identities. Then we'll understand how to simplify expressions using these identities, and this will be followed by a communication-based question. Now, co-function identity is slightly tricky, so I've taken up another question so that we understand this concept better. Now, many times when you simplify two different expressions, you might land up with the same end product. We'll see whether it is really equivalent or not. The most important part is, of course, to prove the trigonometric identities. We'll actually explore more of this in part 2 and 3 of our examination practice. Then working with equations, what I've done here is taken two equations and the process to express an equation independent of theta itself by the method of elimination. That will be the most important question in this particular video. And a similar one will be followed with a bonus question. So I hope that will help you to begin with your exam practice. In practice 2 and 3, our focus will be on trigonometric identities and solving equations. So let's begin with the formula sheet itself. So this is a summary of some formulas which will be used. Two of them will be used extensively. So the very first one is the Pythagorean theorem identity. So Pythagorean theorem, as you know, is a square plus b square equals to c square. In trigonometry, we get three different equations which are sine square theta plus cos square theta equals to 1 plus tan square theta equals to secant square theta, and 1 plus cot square theta equals to cosecant square theta. So these three are very helpful in solving many trigonometric identities. The process normally is to write all the terms in sine and cosine. So tan theta, which is sine theta over cos theta, could be converted. Cot could be also converted to sine and cosine. Once you do that, then the application of Pythagorean theorem helps you to solve the identity itself. Now, talking about converting to sine and cosine, we normally prefer not to work with reciprocal uh, or the secondary trigonometric ratios. We convert them also into sine, cosine, and tan. So the idea here is to convert the reciprocal secondary trigonometric ratios to primary trigonometric ratios. If you have tan and cot, convert them also in sine and cosine. Then you could apply the Pythagorean theorem identity and solve your questions. Let's see how to do it. So in the very first one, we have two examples. The question here is simplify expressions using identities. I would like you to actually solve along with me so that you can check your answers also. So I'll go slightly so that I give you some time to finish your solution before mine. Now here there are two questions. First is cos 2x plus 1 times cos 2x minus 1 is what in a simplified form. The second one is 2 sine squared x times 1 plus cos x whole square plus 1 minus cos square cos x whole square. There is a typing error here. Let me correct that before we begin. There should be a plus sign here. Okay. So let me do this part itself first since there is an error in typing. So I'll rewrite this and solve it here. It is 2 sine square x plus 1 plus cos x whole square plus 1 minus cos x whole square. So we have to simplify this particular term. So the idea is to expand the square terms. We could, uh, now since you see that they are all in cosine, you might tend to even write cos sine square x as 1 minus cos square x. But for now, let me keep it as 2 sine square x. Let us see what do we get from the next two terms. So apply the formula a plus b whole square. So let me write down the formula being used here, which is a plus b whole square, which is equal to a square plus 2ab plus b square. And if it is negative, this is negative, correct? So we get 1 plus 2 cos x plus cos square x. And here we get plus 1 minus 2 cos x plus cos square x. So we get 2 sine square x. Now you can see that the two terms plus and minus 2 cos x, they cancel, right? So you could now write this as plus 1 is 2. And we have here plus 2 cos square x. We could write this 2 as common. And so what we get here is 1 plus sine square x plus cos square x. Now, what is sine square x plus cos square x? It is equal to 1. So we could write this as 2 times 1 plus 1, which is 4. So the expression actually simplifies to a number 4. So in this case, we have really eliminated x itself in simplifying. So many times in the expressions, you might get just a number as our constant as a result. Perfect. So that is how you're going to do it. Now, in this particular case, let me highlight that we did not really expand sine square x. So don't be in a rush to use all your techniques at one time. You can go slowly using one at a time and see what exactly should be done. So as the solution unfolds, we will exactly know what to do with the fundamental techniques learned. Okay, now let's do the other expression. We'll simplify this one, which is multiplication of cos 2x plus 1 times cos 2x minus 1. So it is a plus b times a minus b. So let me write down the formula. We have a plus b times a minus b, which gives us a square minus b square. So you are seeing how we are using algebraic identities to prove trigonometric identities. So they go hand in hand. So that could be written as cos of 2x square minus 1. Okay. Now, you remember the Pythagorean theorem identity, which is sine square x plus cos square x equals to 1. Now we can see what is cos square x minus 1 equals to. So if I rearrange this, we get cos square x minus 1 equals to, taking sine to the other side, minus sine square x. Correct? So we could now write down in the expression form, this could be written as minus sine square 2x. Is that correct? The right way of writing, of course, is what I've written at the end. So that is the simplified form of part A. So the answer for the second one is minus sine squared 2x. Now let's see the communication question. Now here is the next question. It is based on communication. The question is, steps are shown below to prove that sine theta equals to square root of 1 minus cos square theta is an identity. So we are proving that sine theta is equal to square root of 1 minus cos square theta. Find the mistake and provide a counterexample to show that the trigonometric equation is not an identity, right? Actually speaking, it is not an identity. However, we have shown here steps which prove that it is an identity. You need to actually pause the video here and figure out where did we go wrong. And once we know that it is not a trigonometric identity, the best way to show that this is not an identity is to use counterexample. So here we are going to use the counterexample also. Now, as soon as you look at the particular equation, you know that square root of anything will always be positive, correct? However, sine, you know, it is positive or negative, correct? Sine is positive in quadrant 1 and in quadrant 2. However, it is negative in these two quadrants. That clearly indicates that the given equation is not an identity. So there is definitely a mistake here, correct? So let's go through the proof. So the very first statement here is sine square theta plus cos square theta equals to 1. That's a Pythagorean identity. That is correct. No problems. We rearrange sine square theta as 1 minus cos square theta. That's correct. Then we do square root and write down this. Now that is an error. The error here is that whenever you do square root, you have to write plus and minus. So the expression should have been plus and minus, not just plus. And therefore, clearly it is not matching. So this statement is left side is not equal to right side. Since the right hand side does not have plus and minus sign, and therefore we could show that there is a mistake and it is not an identity. Now we need to do part B actually, which is to provide a counterexample. So let me write B clearly here and we say counterexample. Since we were saying that sine could be negative if I take an angle in quadrant 3 or in quadrant 4. So we can actually take theta equals to, let's say, 240 degrees. So 240 degrees will give us the terminal arm in quadrant 3, where the angle will be what? 60 degrees acute angle. So what we get the value here is that sine theta will be sine of 240 degrees, which is same as minus sine of 60 degrees. And sine of 60 degrees is, you can make your special triangle. Sometimes calculator is not allowed. So I'm just doing this without calculator. Okay. So that gives you an angle which is equal to half. So we get negative half as our answer. But if I do for the right hand side, this is left hand side. For the right hand side, the value will be square root of 1 minus the cos value of, let me write, cos square theta, where theta is 240 degrees. So we get 1 minus, cos is adjacent square root 3, so we get 3 over 4. So that gives you equal to 4 minus 3 over 4, all within square root. So which is equal to half. So you can clearly see that left hand side is not equal to right hand side. And that is how you are going to show with the help of a counterexample that this is not an identity. Is that clear to you? Perfect. Next question here is, I've given the heading to understand cofunction identity. The question is, explain the difference between the following equations. So we have two different equations here. One of them is sine 90 degrees minus theta equals to sine theta. The other one is sine 90 degrees minus theta equals to cos theta. Now, what is the difference between these two equations? Let me rewrite them. So we have sine of 90 degrees minus theta equals to sine theta. That is one of them. The second one is sine of 90 degrees minus theta equals to cosine theta. What is the difference between the two? So let's look into our formula sheet so that it reminds you of what we did. We proved co-function identities, I hope you remember, where we are saying that in a right triangle, if I look from the other side of the triangle, the opposite side becomes the adjacent side. And therefore, we could always write sine 90 minus theta as cosine theta, right? So coming back to the question itself, sine 90 minus theta equals to cos theta is basically a trigonometric identity. So this is an identity. It is always true. However, the equation here is a conditional equation. This equation is only true for some values. For example, if theta equals to 45 degrees, we get the same result. 90 minus 45 is 45. So we get the same result. So likewise, we could have some values. But this is true for all values of theta. Is that clear to you? So that becomes a trigonometric identity, and this is a conditional equation. So your answer is that this is a conditional equation, then other one is an identity, and that is how you could show it. The next question here is strategy to simplify and compare the expressions. Simplify the following expressions and explain if they are equal. So it's a very good question. Simple, but it has a lot of content in it. So the very first one here is 1 plus tan x over 1 plus cot x. Since we already have tan x and cot x, it's a good idea to convert cot into tan using reciprocal identity. So I could write this as 1 plus tan x over 1 plus 1 over tan x. And now we can actually rewrite this. So we get 1 plus tan x over, taking common denominator, we get tan x plus 1 over tan x. So these two cancel, and what we get here is equal to tan x. So the result is that this particular expression is actually equal to tan x. Now let's look into the other expression, which is square root of 1 minus cos square x over cos x. Now 1 minus cos square x is, as we learned, sine square x. So we have sine square x over cos x. Square root of sine square x is always, this is always a positive quantity. So we should write this as what? The numerator actually is not just sine x, it is absolute value of sine x divided by cos x. Well, that does give you tan x. Cos x could be positive or negative. So that could simplify to tan x. So we do get tan x as a result. Now the question is, simplify the following expression and explain if they are equal. We do get tan x and tan x after simplification. Now the idea is, are they equal? If they are not, provide the reasons. Now in this particular case, the reasons are that they have different restrictions. So for example here, what are the restrictions? You have to look into restrictions. For any trigonometric identity, you cannot just multiply by 0. You could have restrictions in your equation. And within those restricted domain, the identities are proved. Now here, we have a restriction that cot x and tan x, they are undefined for some values, right? So the value of x is not equal to n pi by 2, multiples of pi by 2, correct? I should write, or you can say we are working more in degrees. So multiples of 90 degrees, 90n, where n belongs to integers, correct? Since either tan x will be infinitely large or cotangent will be infinitely large, and so we cannot use those values. Now in the other case, we have only cos x in the denominator. So cos x is not equal to 0. You cannot divide by 0. And therefore, in this particular case, cos x is 0 as odd multiples of 90 degrees. So it is 2n plus 1 times 90 degrees, which are the restrictions, right? So in this case, the value of x is not equal to odd multiples of 90 degrees. You get the idea. So that is the difference, and therefore the two expressions are not equal. You get the idea, right? So they are not equal. So the answer will be they are not equal because they have different restrictions. So let me write down the answer here. Different restrictions. So if you say that if the two equations are being compared where the value of x is not integral multiple of 90 degrees, in that case they will be equal, but not as shown here. Perfect? Now let's take examples based on trigonometric identities. We'll actually explore more in part 2 and 3 of our exam practice on trigonometric identities. So here is a simple one to begin with, I should say. Prove the following trigonometric identities. Sin x tan x equals to secant x minus cos x. The other one is 1 over 1 minus sin x plus 1 over 1 plus sin x is equals to 2 secant square x. So let's take the very first one now, which is sin x tan x equals to secant x minus cos x. So we can begin from any one of these two sides. Both are equally complicated or simple, you can say, but let's begin with left hand side. It seems to be more complicated. So left hand side here is sin x tan x. Tan x can be written as sine over cosine. So we have this as sin x times sin x over cos x. So that gives you sin square x over cos x. Sin square x is 1 minus cos square x divided by cos x. Correct? Now we could write this as 1 over cos x minus cos x, which is same as the right hand side, which is 1 over cos x is secant x minus cos x. So we have shown that left hand side is equal to right hand side. Is that clear to you? So we began with the left hand side and then we showed that it is equal to the right hand side. So that is how you are going to do it. Perfect. So I hope the steps are absolutely clear. So we could write here also, there was space. Secant x minus cos x, which is equal to right hand side. Clear? Now let's take the second identity, which is 1 over 1 minus sine x plus 1 over 1 plus sine x equals to 2 secant square x. So we'll begin with the left hand side in this case clearly. We can take common denominator, which is product of 1 minus sine x times 1 plus sine x. Cross multiply, you get 1 plus sine x plus 1 minus sine x. And now add the like terms. 1 plus 1 is 2, sine x minus sine x is 0. And the denominator we get 1 minus sine square x. So you've seen that many times we are working with this particular formula, which is sine square x plus cos square x equals to 1. It could be written in many different ways. So we have seen now that cos square x equals to 1 minus sine square x. So the denominator is actually cos square x. And 1 over cos square x is secant square x. So we get this as 2 secant square x. And that is the right hand side. And so we have shown that the left hand side is equal to right hand side. And that is how you prove identities. So begin with right hand side and end up showing that it is equal to the right hand side. So we begin with the left hand side in this case, and we have shown that it's equal to right hand side. So that is an identity. Perfect. We use the Pythagorean trigonometric identity in sine to prove it. Now we come to a very difficult question in this particular test paper, which is an expression independent of theta. Write an expression independent of theta from the following set of equations. So we are given two equations here. One is x equals to 3 sine theta. The other one is y equals to 2 cos theta. Now how to do these examples? So let me rewrite the equation. It is x equals to 3 sine theta and we have y equals to 2 cos theta. We know the Pythagorean identity, which is sine square theta plus cos square theta equals to 1. So as you can see here, if I get two terms as squares of these, adding them will give me 1. So 1 is independent of theta. So that is the whole concept. So elimination to make it independent of theta is this concept. So what we need to do as a strategy here is, in our equation, we have to isolate the cosine and sine terms. So when you do that, you could rewrite this equation as sine theta equals to x over 3 and cos theta equals to y over 2. And now you could substitute these values since you know that sine square theta plus cos square theta is actually equal to 1. So we can substitute these values. You get x over 3 plus y over 2, right? So we have to square them definitely. Should be equal to 1. So when you square them, you get your result, which is independent of theta. So you get x squared over 9 plus y squared over 4 equals to 1. That looks like an ellipse, right? So most of the time, that is what you're supposed to do. Sometimes you may be required to write in a particular form, but that is how you could do it. You could actually cross multiply. You can write 4x squared plus 9y squared equals to 36. So that could also be your answer. So either way, you could write your solution, but you can see here that in both the cases, the final equation, let me write final combined equation, is independent of x. Now that's a huge concept, and we can now understand that you could represent an ellipse as a parametric equation, right? So these are also called parametric equations. Let me like we'll discuss more about parametric equations in another unit. Now let's take the bonus question, which is if a over sine theta equals to b over cosine theta, find the value of sine theta cos theta. So you can actually now pause the video, find the value of sine theta cos theta. So let's see how to do it. The question given to us is a over sine theta equals to b over cos theta. We can say let it be equal to k, right? That's the strategy. So from here we can write that sine theta is equals to a over k and cos theta is equal to b over k. Does make sense to you, right? So that's a very good strategy to work with. Now we also know, as we learned earlier, that sine square theta plus cos square theta is 1, right? So, so we can, or we just need to find the value of sine theta cos theta. So we know what do we need to find. We know we want to find sine theta cos theta. So sine theta cos theta will be product of these two. So a over k times b over k. So it is basically ab over k squared. So that is what it is. How do we find the value of k now? That becomes a big problem. To understand this, we understand that it is a times b and divided by k, which we get. So clearly, we do have to use the concept of sine square theta and cos square theta to relate a and b and k, right? So let's see what it is. So we can now write down that sine square theta plus cos square theta is equal to 1, and that gives you a square over k square plus b square over k square is equal to 1. So k is common. That means a square plus b square is equal to k square. So we get the value of k. You get the idea, right? So sine square theta plus cos square theta is 1, but we know sine theta is a over k, cos theta is b over k. So replacing them, we get here a square over k square plus b square over k square is equal to 1. Taking common denominators, we get a square plus b square is k square. And therefore, we can write down our answer, which is sine theta plus cos theta is equal to ab over a square plus b square, right? So we substituted the value of k square as a square plus b square in our expression. So that is how we are going to solve it. So I hope that makes sense, and that is how you could do such questions. So that becomes our bonus question for exam practice 1. I hope you have understood all the concepts, especially these particular equations, the fundamental identities, and how we can actually use these fundamental identities to simplify expressions, to solve equations, modify them, make them independent of theta, and to prove identities. We also understand that Two identities which simplify to the same expression, saying tan theta in this case, may not be exactly the same since they may have different restrictions, and that's a very important learning. With this, we end the video. Get prepared for examination practice 2 now. Thanks for your time and all the best.